Okay, so one quick administrative announcement. Actually, two quick administrative announcements. So I'll do the second one first. Is the drop deadline this Friday or was it last Friday? It was last Friday. Okay. It's this Friday. If you have any concerns or questions about possibly dropping this class, I would very much appreciate the chance to talk to you before you make a decision, either to help you decide if you want help or if you've just decided, no, screw it, I'm dropping out. Not so much that I can talk you out of it, but just so that I know, I have some idea why. If there's something that you think it's just going badly, it's not a good match, something that we're doing that's not working for you, it's better for us if we know, so that if there's a problem that we can try to address either this semester or in next semester when you take it again. We can't fix the problems if we don't know what they are. So if you do decide to drop, please come by office hours on tomorrow or send me email or something just to let me know what you're thinking. The more complicated administrative thing is that we are launching the peer evaluation experiment. Possibly with the exception of setting up an anonymous Gmail account if you think that's necessary. I'm expecting this is probably going to take about 20 minutes this week and maybe an hour next week. Okay. So the idea is that for one of the questions on homework 6, you will submit, as you normally do, a written solution with group names and IDs at the top. But you will also submit to this CrowdGrader site an anonymous individual submission, meaning every individual student will submit a copy of the solution without your name on it, or your net ID, or your section number, or the Gmail address you use to log into CrowdGrader. CrowdGrader has a mechanism where you can identify other members of your group. For privacy reasons, that identification needs to be done using whatever Gmail address you use to log into CrowdGrader, not using university IDs. And then after the submission deadline, there'll be a redistribution of the submissions so that each of you will be asked to review 5 submissions and supply a grade for part A and part B on a scale from 0 to 4. How correct is this? On a scale from 0 to 4, how clear is this? These grades are meant entirely as feedback from you to each other, and the course staff will also be submitting solutions, and we will also be submitting reviews. Even though we're asking you to assign a number, this number will not be used in any way to affect your semester grade. Partly because CrowdGrader does some interesting statistical things with those numbers before it reports them, and partly because we just don't know how accurate the crowd assessment of each other's homework is going to be. However, we are setting as a prerequisite that you submit something and that you submit reviews in good faith in order to get credit for this homework problem. The grade on the homework problem will be determined by the course staff as usual. Okay. So the point of this exercise is really just to give another feedback channel to you. That the review cycle will be about 2 days long. So you'll submit your homework on Tuesday, and you'll have 48 hours to look at 5 other people's solutions and give them scores. This is the part where I think will take about an hour, right? About 10 to 15 minutes looking over each submission, maybe 20 minutes for the first one and 5 minutes for the last one. This is partly an experiment for next semester when there are 400 students taking this class. And we're anticipating that we may not be able to get homework graded as quickly. And so it's much more important for the students to get some form of feedback as fast as possible. And partly because we believe that asking you to critically evaluate other people's submissions, not only for correctness, but for style and clarity and so on, will help you think more carefully about how you write your own submissions. So for each of those scores, we're also going to ask you to write a sentence or two of narrative feedback about why you think this deserves a 2 out of 4, why you think this deserves a 4 out of 4. And it's actually that narrative feedback that is hopefully the most valuable byproduct of this whole thing. Not both, but you're getting that narrative feedback from other people in the class who can tell you, no, really, I don't understand what you wrote here, or, wow, this is fantastic, this is much better than the submission I put in. And just so you're in that critical frame of mind of when you're writing, keeping in mind that other people are going to be looking, and the way they might look at it might be similar to the way you might look at it. As I said, this is not something that the actual submission grades, the actual review grades that CrowdGrader assigns are not going to affect your grade in 374 unless they're zeros, in which case you won't get credit for homework 6 problem 2. Okay? Detailed instructions, how to sign up on CrowdGrader, how to submit stuff, how to review stuff, how to identify other people in your group. Those should all be posted to the course website by the end of the day today. We are doing a dry run where we will ask you, first, sign up. Second, answer this incredibly hard homework problem, which if I remember correctly is what is 2 plus 2? Just to get you through the mechanics. And then we will ask you over the weekend to review 5 other people's answer to what is 2 plus 2, just to get you used to the reviewing mechanisms so that we can shake out any misunderstandings or any bugs before Tuesday's actual homework assignment. Okay. Did anybody have any questions about this? Again, I have to say thank you in advance for being guinea pigs. This is an experiment. We think it will be useful and helpful for you, but of course, we will have to ask you after the smoke clears. We'll probably do this 3 or 4 times between now and the end of the semester. We'll have to ask you whether you actually believed that, whether you actually agree with us that this was useful, to get the feedback quickly and to have the practice in reviewing each other. Okay. If questions arise, please send me email, post to Piazza, talk to talk to us in office hours, talk to us after class. Okay. Okay. So for the last several lectures, we've been talking about backtracking algorithms and dynamic programming algorithms. And the basic idea behind these, what a backtracking algorithm is you need to make some sort of relatively simple choice that reduces the original problem that you're asked to solve to a smaller instance of the same problem, and then recursively solve everything else. So, for example, if we're asking about the subset sum problem, here's a set of numbers. tell me whether there's a subset that adds up to a particular value. The simple choice that you make is, here's one element out of the set. Is it in the subset I'm looking for or not? And if a little birdie landed on your shoulder and told you it's not, then you could recursively solve the rest of the problem. If a little birdie landed on your shoulder and said it is, then you could recursively solve the rest of the problem. But because there are no little birdies flying around in your computer, you actually have to try both options, right? So instead of actually sort of guessing what the correct choice is, you enumerate all the possible choices that you could make. Yes, it's in the subset. No, it's not. And then for each possibility for that choice, you attempt to recursively solve the problem. And then at the end, you evaluate which of the choices was in fact the right one to make. Okay? Longest increasing subsequence. Do I include this element in my sequence or not? Let's see. What was one of the NFA acceptance? Should I transition to this state or to that state or to this other state? I don't know. Let's try each of them, and for each choice of which state to transition to, recursively try to accept the rest of the string starting at that state. Okay? In the magical land of non-determinism, you make this choice by magic. You just non-deterministically know the right answer. Or you imagine spinning off a separate parallel thread for each possible choice, and if a particular thread ends up failing, you just kill it, and only the surviving threads are the ones that actually produce output. But we don't have infinite parallelism, and we don't have a magical clairvoyance, and we don't have little birdies, so we have to try them all. Okay? Now, it is really tempting. It's incredibly natural, it's incredibly common, it's incredibly tempting to try to short-circuit this process. Rather than try all options, and this is really brute force, is to actually just choose one option and then recursively solve everything else. Okay? So somehow, for example, longest increasing subsequence, you look at the number and you say, yes, I should include that, and you go on from there. You commit at the beginning, and you just recurse to finish off the computation. Right? If I'm trying to compute edit distance between two strings, if I notice that two characters are equal, then I say, yes, I should accept those as my first edit operation should be this free replacement. I should replace an A with an A that costs me nothing, and then recursively do everything else. Now, that's making a greedy decision. You're being clever as a way of optimizing the recursive brute force backtracking thing that's underlying the dynamic programming algorithm. If you're very, very lucky, this will work. Most of the time, you will not be very, very lucky. Okay? So I really want to make sure, I mean, the reason, honestly, the main reason why I'm describing greedy algorithms to you in this lecture is a defensive measure. I want to show you what is actually required to show that a greedy algorithm works. And to establish as a matter of course policy, if you use a greedy algorithm and you do not prove that it is correct, you get a 0, even if the algorithm is correct. So I'm applying by analogy a safety rule inherited from firearm safety. How many of you have ever used firearm? What's the first rule of using firearm? Because it's loaded. Rule 1, the gun is loaded. It will go off if you point it at things. Unless, there's an exception, you unloaded it. If you open the chamber and see, look, there are no, everything, there's no ammo in this weapon, then you can say, okay, I know it's not loaded. Now, nobody else will know that it's not loaded, which means if somebody points a gun at you, they mean to kill you. React accordingly. Unless you unloaded the gun, which means, yeah, when you're on set at a movie, everybody on set should unload the gun. Otherwise, people get hurt, people get killed. Same thing. If you use an algorithm, it doesn't work until you unload it, meaning until you prove that it works. And for most algorithms, this is actually not much of an issue. I'm really applying this particularly defensively for greedy algorithms because it is so tempting to say, oh, well, of course, when I'm dividing a string into a bunch of smaller palindromes and I want to keep the number of palindromes small, of course, I should look for the longest palindrome. Pull that out and recurse on everything else. No, you've made a greedy choice there. You have to convince me that that will actually work, especially because I happen to know that it won't. Okay? This is a loaded weapon until you prove to me that it's unloaded. Okay? So I need to show you how to actually prove that a greedy algorithm is unloaded, because otherwise you implement an algorithm and it's wrong, somebody's pacemaker stops, somebody's bridge collapses, somebody's spaceship flies into Mars. Yes, that actually happened. Somebody's plane crashes. It wasn't actually, the thing that made the spaceship crash into Mars was not because they inappropriately used a greedy algorithm. It was something much more basic. This particular space probe was an international collaboration involving people in the European Space Agency and people at NASA. And the people, when they wrote the software in various places, the Europeans wrote software that assumed metric units, and the Americans wrote software that assumed American/Somali units. Were the only, miles instead of kilometers. So the probe said, oh, look, Mars is 100 kilometers away, and the American software said, great, 100 miles, I can accelerate this fast, and went into the planet. Okay. So, lesson, use metric. The United States has been officially on the metric system since 1972. This is the reason why Coke comes in 2-liter bottles. Why do we use 2 liters? Because we're officially on the metric system. I have no idea why we still buy gallons of gas or gallons of milk. But you can't buy gallons of Coke. It's weird. All right, so let me give you an example of a greedy algorithm problem, a problem that's solvable by a greedy algorithm. And this is an example that is, again, from the mists of history, because most people don't actually see anymore. So back when my dad was a grad student, old electronic files were kept on huge reels of magnetic tape. Right, you still occasionally see this in the movies where you've got this bank of computers and there's these things that look like wheels spinning back and forth. That's magnetic tape, right? And the difference between tape and disk, or between tape and flash memory, is that tape is inherently not a random access medium. If I want to read a file off the tape, I have to physically wind the tape until the right portion of the tape is under the read head, and then read the file. Okay? I guess I should ask, how many of you have actually, had music on a cassette tape? Okay, good. Good. I'm not that old. It's like that, right? You want to find your favorite song on the tape. You have to wind the tape to the beginning of that song before you hit play. Now, for the idea for the sorting problem is, I want to imagine that I have a bunch of files of various lengths, and I'm going to be given those lengths as just an array off to the side. And I want to sort the files on the tape into a particular order so that if someone asks me for a random file, or asks me for each one with exactly probability 1 over n, the expected amount of time that I have to spend winding the tape to the right spot, reading the file, and then winding the tape back to the beginning is small. Okay, so I'm going to ask you for a random song on your mixtape. You need to sort the files on your mixtape so that you spend as little time as possible winding and rewinding. Okay. Now, this is actually a problem that has real applications in computing. How many of you have been to the tour of Blue Waters? Not enough. So we try to figure out a way to go see Blue Waters. So it looks like something off of the set of a science fiction movie, except much, much louder. Basically, you get these giant black refrigerator-looking things with pipes running overhead. It's incredibly loud because of all the water being pumped through the computer to cool it off. But there's very little to see. There are no blinking lights on the front that actually tell you anything is going on, except in one part of the room, which is half the size of a football field. The tape robots. So the amount of data that Blue Waters has to manipulate is measured in petabytes. And so rather than disks or memory of any kind, they have banks and banks of I think it's 4 terabyte tapes. And they have a robot that has an arm that goes, it looks like a Japanese vending machine. I've probably now told you more about what a Japanese vending machine looks like than a tape robot. But it looks like you imagine, a robot to look. There's a thing on a track that runs horizontally, and there's a gripper that goes vertically. And every so often, you see this thing zip down the track, grip, and grab a tape and zoom down to the other end and pluck it into a reader. Okay. Because that's the fastest and most reliable way to store that much data. Okay, so being able to get actually to the right tape and also being able to get to the right file on the right tape is a fairly critical importance dealing with data of that size. Okay, so what I want to sort, meaning I want to find some permutation, we'll call it pi, that minimizes the total cost or the expected cost of looking for a random file. To keep things simple, let's just imagine I'm going to look for each file once in some order I don't know, and I have to reset at the beginning. So I'm going to be looking for every file from 1 to n. Something that I'm going to look for every file from k to n. And then the cost that I need to spend to look for the kth file on the tape is the lengths of all files up to position k, wherever the kth file is, which is the position of the kth file is going to be given by this function pi of the length of the ith file. Okay? So that sum, that double summation, is the total time that I need to read all n files one at a time and reset the tape to the beginning after each read. Okay? So when I read the first file in the tape, I just read it and go back. When I want to read the 8th file in the tape, I have to read through the first 7 as well before I get to the 8th file. Everybody understand what the problem is? K is the index for the outer sum. So I want to do this for every file. For every file, I have to read every preceding file. Right? And then pi is the position of the kth file on the tape. So I have to read all files up to and including that position, the file in that position. Okay? Yeah?
So are you like rewinding or you continue with the outer summation?
I'm sorry?
Are you like rewinding before you continue with the outer summation?
Yes. So I'm ignoring a factor of 2 in here. You read forward up to the file in position pi of k. You read the file at position pi of k, and then you rewind. Okay. Let me make sure that I've actually got. Actually, I think I'm screwing up the indices a little bit here. So let pi be the identifier of the file at position I. Okay. Then I think this is a little bit more coherent. Okay. All right. So what order do you think I should use? All right. So for example, if I have the files ordered like this, I have to read this file 3 times, this file twice, and this file once. But maybe I can put the files in a different order. So this is A, B, C. But if I write it as B, A, C, now I have to read B 3 times, A twice, and C once. So what order do you think is going to be the right one? Put the shortest stuff first. Right? Now, if I were thinking about this as a backtracking problem, I would say, I don't know, let me try them all. And ultimately, as a backtracking problem, I would end up trying every permutation and figuring out what, for every permutation, what the value is here. But the claim is that the shortest file is the one I should put first. I'm making a greedy decision now, and then recursively do everything else. In other words, sort the files in increasing order of length. Okay, so claim, just sort L. It gives you the, sort the lengths, and that will give you the correct order. Okay? Another way of saying that is that the length of the file in position I should be less than or equal to the length of the file in position I plus 1 for all I. Okay. Now, that's a wonderful claim, and as it happens, it is correct, but the gun is loaded, so we need to actually unload it before we're willing to deploy this algorithm on our $250 million supercomputer. Okay, so here's how we prove this. I'm going to do it. I'm going to use a proof by contradiction. I'm going to say, let's suppose there's some other ordering whose cost is cheaper. Okay, so assume in the optimal ordering, that I have L of pi I is bigger than L of pi I plus 1 for some integer I. In other words, as I scan through the tape, I see at position, at position I plus 1, I see a long file before a short file. Okay? Let me call for just to simplify things, I'm going to call this file A and I'm going to call this file B so I don't have to keep saying pi of I plus 1. Now imagine, if you will, swapping these two files on the tape. Okay, so now file B is in position I and file A is in position I plus 1. Now the cost of each of these permutations is given by this double summation at the top. So what I want to try to do is figure out what effect that exchange had on this function, on this total cost function. Okay? Now, this is not as complicated as it might look, because most of the changes, all the changes are actually fairly local. So if I look at a file X sitting out here at the end of the tape, has the cost of reading X changed at all? No, right? In fact, getting to the end of position I plus 1 hasn't changed. So anything that's beyond that is in exactly the same position on the tape that it was before I did the exchange. Similarly, if I have some file Y earlier in the tape, the cost of reading Y hasn't changed. Okay? The only files where the cost has changed are A and B. Okay? So how much has the cost of reading A changed? It's increased by the length of B. Okay? So the cost of reading A increases by the length of B. And how has the cost of B changed? The cost of B has decreased by the length of A. So the total change, the total cost, has, let's say, increased by length of B minus length of A. Right? There's an increase in the total cost of length of B coming from accessing A, and there's a decrease of length of A coming from accessing B. So the overall change in the cost, if I make this exchange, is L of B minus L of A. Except L of A is bigger than L of B by assumption, so this is negative. The cost has gone down. Now, notice at this point I have a contradiction. I started out by saying, suppose in the optimal ordering something is out of order. Then I changed the ordering and my cost function went down. But optimal meant the lowest possible cost. So I can't go down. Right? The only way to resolve this is to conclude that this assumption that I've written at the top of the page is false, which is what we tried to prove. Okay? So the basic strategy here is assume that, in fact, the greedy algorithm didn't work. Assume that the greedy algorithm gave you something that was not optimal. Change it slightly. Change the solution that the greedy algorithm computes, or change the optimal solution very, very slightly to make it look more like the greedy solution. And then argue that that made the solution better. So the conclusion from this is if you do anything other than the optimal algorithm, if you do anything other than the greedy algorithm, the result that you get can be improved. The only way to get a solution that you cannot improve is by running the greedy algorithm. Okay? This is called an exchange argument. Argument. Okay. So again, at a very high level, consider any non-greedy solution. In this case, a solution means a permutation of the files. We'll perform an exchange to make the solution look more greedy. And finally, and here I really mean argue, finally argue that the new solution that you get after doing the exchange, now the way it happened in this particular case, the new solution was better, but in fact, it's enough just to prove that the new solution is no worse. Okay. In this case, doing the swap strictly reduced the cost. It made the solution better, which means that the strategy, sort the files by increasing order of length, is the only way to get an optimal ordering for the files. In other problems, the greedy algorithm may not be the only way to get the optimal solution. Yes?
How would an algorithm change it?
Excellent question. What would happen if you had frequencies in addition to lengths? Okay. Before we get to that, let me make sure that everybody sort of understands the outline of how an exchange argument works. Okay. So now suppose now files on the tape have length L from 1 to n and frequencies F from 1 to n. And now my total cost is the sum over all files of the time it takes to read that file times the number of times I'm going to read that file, the frequency. Okay, so I'm going to get a summation that includes in the inner term both it's the product of frequencies and lengths. Okay, so this is my cost now. I sum over all possible positions, K, of the total cost that I can charge to accessing the K. Sorry, that should be, this last one should be an I. So I'm going to read file K, F, the file in position K, F of that many times, and each time I read the file at position K, I also have to read files at earlier positions leading up to K. Okay, this is my new cost function that I want to minimize. Now we already know that if we only have lengths but all the frequencies are 1, we should sort by increasing order of length. What should we do if all the lengths are equal but the frequencies are different? Right, we'll sort by actually decreasing frequency. We want the most common files to be at the beginning of the tape. The files that we're going to look at the most often need to be as accessible as possible. Okay? So intuitively, we either want to sort by increasing length or by decreasing frequency. But now we're given both. Now we're given lengths and frequencies. And there's a tension between them because it's possible that increasing length and decreasing frequency will not give you the same order. So perhaps there's something else that I can sort by that somehow combines lengths and frequencies.
Like we can have like a weighted.
So can you be more specific? What?
We had a file of 2, like 2, and we have.
Oh, so you want to sort by the product of these two? Do you want to sort up or down?
Biggest one.
Okay, so then that will be wrong when all of the lengths are the same, because then you want to sort. When all the lengths are the same, you want to sort the product down. When all the frequencies are the same, you want to sort the product up. But you're close. Very, very close.
So if like one file,
Huh?
why don't we just take it, I mean, stick these files at times and consider that as one file, and then do the previous thing again?
Because that has the opposite effect. So I have to be very careful here. Frequency does not mean how many times I'm going to access. The frequency means how many times am I going to access this. When the frequency goes up, that means I'm going to access it more times. I want things that I access more to be cheaper, so that they'll affect the sum less. So I want the more frequent things intuitively to be close to the beginning. What you're proposing is to penalize the more frequent files by making them longer. That's exactly the opposite of the effect I want, because that will push the more frequent things to the end. Yeah?
Can you sort the lengths within the frequency?
Yeah, that won't quite work. Because if the lengths are just barely off, then, and the frequencies are way off, then you really want the frequencies to be more significant, and the other way as well. Somebody hasn't suggested the wrong solution yet. Yeah.
Can you take the ratio?
The ratio, that's the correct solution. So sort by length over frequency. Now, about half the time when I give this example, someone suggests sorting by length minus frequency. The function, it goes up with length, it goes down with frequency. At which point I assume every engineer in the audience is cringing, because you can't add inches and hertz. Remember the dimensional analysis from physics? If you ever find in your solutions that you need to add newtons with seconds, you're doing something wrong, because newtons and seconds don't add. Exactly the same thing is going on here. So you sort by the length divided by the frequency. And I won't go through the details of the argument, but except to give you the punchline, swapping adjacent files A and B increases the cost, increases this cost function by length of B times frequency of A minus length of A times frequency of B. And so if A and B are out of order according to this ratio, this will be a decrease in cost. And that otherwise the argument is exactly the same as we did with just lengths. All right, so here's the entire argument in the notes. Boom, boom. There it is, 1 inch long. I'll just let you read it. Okay? So again, if I pick anything that's not greedy, I find something that's out of order. By swapping them, I made the cost go down, so that thing I started with could not possibly be optimal. The only way to get the optimal permutation is by following the greedy algorithm, which sorts by this function. Okay.
Question.
Yeah?
What is the cost of swapping? Is it A plus B or B plus 2?
So I need to distinguish between two things here. I'm trying to figure out what order to write the files on the tape. When I'm solving that problem, I have not actually written the files on the tape. I'm just trying to figure out what order to do it. So the cost of actually doing the swap is 0. right? Because I'm not actually moving files on the tape. And the units of cost is seconds I need to move things on the tape, not nanoseconds I need for my algorithm to run. Okay. So this is a sorting algorithm. It takes n log n time. So I guess in that sense, you can say a swap takes constant time if you decided to sort by swapping. But that I don't have to specify that. Right. Okay. So let me describe the second problem somewhat farcically. So let's imagine that the university decides to open a new major, which, for lack of a better term, I'll refer to as CS plus Frisbee. And the degree requirements for CS plus Frisbee involve, as with all university degree programs, taking a certain number of classes, a certain number of hours, and a certain number of categories. But it's been determined that, in fact, the bulk of the degree is earned by just taking a certain number of classes from a particular list. And it's well known that none of these classes require any actual work. Okay? However, the university has a restriction that without the instructor's permission, you cannot register for two classes whose meeting times overlap. And, well, because none of the classes require any work, they also don't require any work by the instructors. So all the instructors are off on a beach in California somewhere. You can't reach them to get that permission. So it's not possible to register for more than one class at a time. And the classes are totally weird. One of them meets, 7:30 in the morning until 11:52. Another one meets from 11:50 to 11:59. It's not like you have to actually go to the classes. Remember, you just need to be able to sign up. And your goal is to sign up for as many classes as possible. Okay? So somewhat more formally, you're given a collection of intervals that have a start time and an end time. And you want to choose a subset of those intervals such that no pair in your chosen subset overlaps. And you want that subset to be as large as possible. Okay? Now, starting on Thursday, we'll be thinking about graphs. You can model this as a graph problem where the intervals are vertices and two vertices are connected by an edge if the corresponding intervals overlap. And now what you want to choose is a subset of the nodes that is as large as possible, and no two chosen nodes are neighbors of each other. Unfortunately, by putting it in that formulation, I've made the problem NP hard. And, if you're CS plus Frisbee majors, your head just exploded. Okay, so don't want to do that. We want something simple. And it turns out that something simple will actually work. Okay? Now, the problem, as we'll see tomorrow in lab, is that there are about a dozen simple things we might do. You might say, I should register for the shortest class, throw away anything that conflicts with it, and recurse on what's left. I might say, take the class that starts earliest, throw away any class that conflicts with it, and recurse on what's left. I might say, find the class that's longest and throw it away, unless it doesn't conflict with anything, in which case I should register for it and then throw it away. Right? These are all perfectly reasonable sounding greedy algorithms, but they don't work because we can't prove that they work. Okay? So, anyone suggest maybe a way to solve this problem? Yeah. Pick the class that ends earliest. All right, so I didn't actually do that with this example. So the class that ends earliest is this one. All right, so I want to choose that class. And then I'll throw away anything that conflicts with that class. And then I'll recurse, which means, again, I'll choose the class that ends earliest. And then I'll throw out anything, well, that's already gone, that conflicts with it. And then I'll choose the class that's still alive that ends first. It's this one. Throw out this, and then this one, and then this one. Okay? So the example on the screen almost followed that greedy strategy. It just made a slightly different choice for the earliest class. Okay? So choose earliest starting time, earliest end, and then recurse after throwing out classes that conflict. Okay? So if I want to maybe visualize this algorithm a little bit more interestingly, I might do it like this. So the way you would implement this algorithm is you would sort the classes by their finishing times. Okay? Which involves sorting the array F of finishing times and permuting the array S. So whenever you swap two finishing times, you swap the corresponding starting times to maintain their correspondence. And then I'm going to just use a simple for loop in order from earliest to latest finishing time. If the class that I'm looking at doesn't conflict with the last class I signed up for, sign up. If it does conflict with the previous class I signed up for, throw it out. Okay? So I'm going to scan through the list of classes in order. The first time I'll say, okay, nothing conflicts with with class 1, so sign up. Class 2, it conflicts with class 1. Class 3 conflicts with class 1. Class 4 conflicts with class 1. Class 5 doesn't conflict with class 1. So that becomes the new class that I test conflicts for. And so here's the code down at the bottom. It's just a simple comparison to decide whether or not to sign up for the class. If you do decide to, I increment this counter, and I add the index of that class to my evolving schedule X. Okay. So because of the sort, the algorithm runs in log n time. If you're lucky and the times fit into some nice discrete distribution of numbers, like only on the half hour, only every 5 minutes, you might be able to get rid of this log. But I said, arbitrary times. It turns out that one of the more popular classes ends at pi o'clock on the dot. So why should I believe that this schedule is actually optimal, that this is the largest number of classes that I can sign up for out of the given set of intervals? Well, I have to prove that. Okay, now, it turns out that, I used the same example above and below, just, reordered the intervals vertically. What I'm not claiming is that the greedy algorithm is the only way to get the optimal schedule. So the schedule that's in gray has the same number of classes as the greedy schedule, which is scribbled over in orange. And I'm claiming the greedy schedule is optimal, which means the gray schedule is also optimal, even though it's not the one produced by the greedy algorithm. So this is a strange bug in English. When I say I want the best schedule, if there is a tie between two schedules for which one is the best, you give me either one. What I really mean is I want a schedule that is no worse than anything else. But because it's more words to say that, I'll pretty much always say the best, the optimal, even though it's not necessarily, the solution's not necessarily unique. Okay. All right, so focus. Focus. There we go. Should try. Focus. Okay, so how do I actually prove this? Really, this is, I want to think of this as a recursive algorithm. I want to think of this as a backtracking algorithm where the simple question I want to ask is, what class do I take first? And the little birdie lands on my shoulder and say, take the one that ends the earliest. And then flies off, and I say, great, and I recursively do everything else. It's a recursive algorithm. So how do I prove things about it? By induction. Okay? So here's what I want to prove. Does anybody know the difference between a lemma and a theorem? Lemma starts with L. Let's call it maximal conflict-free schedule. Includes class that ends first. Okay? What this lemma is saying is that the greedy algorithm makes a choice that is consistent with the optimal solution, an optimal solution. Once I have this lemma, the correctness of the algorithm as a whole follows by the induction hypothesis. Remember, the induction hypothesis is the algorithm works for smaller inputs. Okay? Once I've chosen the class that ends first, that's consistent with the optimal solution. And then by the induction hypothesis, when I recurse on everything that doesn't conflict with this, I get the optimal schedule for the rest of the classes. And then by gluing this back in, I get the optimal schedule for the entire collection of classes. Okay? So this is really the key to the inductive proof, is just showing that the first choice is correct. Okay? All right. So here's a proof. I will show you the entire proof in the lecture notes. There it is. But I'll go ahead and write it out. Okay? So let F be the class that ends first. Okay? This is the class that the greedy algorithm says I should take at the beginning. And then consider any schedule X that excludes F. Okay? So I'm going to pick any schedule that does not make the first greedy choice. And now I want to argue that by doing an exchange, I can at least not make anything worse. So I need to pick out a class from X I can swap out, and another class that I'm going to swap in for F. I'm going to swap in F, I'm going to swap something else out. Okay, so let G be the first class, the class that ends first in X. So please forgive my grammar. Okay, so F is the class that the greedy algorithm would choose first. G is the class that this other guy decided to take instead. Okay? So, by definition, F has to finish before G does. In fact, before anything else does, but definitely before G. So, any class that overlaps F also, sorry, let me say this carefully. implies that F does not overlap any class in X without G. Now remember, G is the class that ends first in the schedule X. Every other class in X starts after G ends, and therefore starts after F ends. Okay? So that means X minus, if I take out G and I add F, this is a valid schedule. And it has exactly the same number of classes in it. In other words, I haven't made anything worse by exchanging D and F. Okay, so in particular, if X is a maximal schedule, if X is an optimal schedule, then this new schedule Y is also an optimal schedule. Now this is only one of the two cases of the argument. There is one other case that I need to consider. Anyone? It's a trivial case, so it's easy to consider it, but I do need to consider it. What if X is empty? Then there isn't a first class in X, because there isn't any class in X. So what do I do then? How do I argue that by including F, I don't make things worse? How many classes do I take if I don't take any classes? 0. How many classes do I take if I take F? Which is better? 1 or 0? 1, because I want to take as many classes as I can so I can get out of this stupid theoretical degree on CS and physics and actually go play disc. Right? Okay? So remember, the goal is to take as many classes as possible, so taking F is better than taking nothing. Right? If X isn't empty, then I follow the rest of the argument. Find the earliest class in the other schedule, swap it out, swap in F instead, and that doesn't make things worse. Right? And that's all you need to prove. By being greedy, I don't make things worse. Now, in the notes, I actually sort of unroll the induction a little bit, and I give another version of this proof, which says, look for the first place where my schedule disagrees from the greedy schedule, and then update it so that at that place I follow the greedy schedule, and that will not make things worse. So by induction, I can replace every class with the corresponding class in the greedy schedule, and never make things worse. So eventually I end up with a schedule that's completely greedy and is still optimal. Okay? So here is my exchange. By swapping out the earliest class in your schedule with the earliest greedy class, I don't make things worse. So if you have an optimal schedule, making it look more greedy, it's still optimal. Right? Now, in the homework, in fact, for the problem that you will submit to CrowdGrader, I generalized this problem by saying, suppose now, in addition to just wanting to take as many classes as possible, each class gives you a certain number of credits. And again, these are weird. This class gives you square root of 2 credits. That gives you, 1.02. This gives you 5. And it may be that the classes that are really long give you the most credits, and so there's some tension between how should I take short classes that don't conflict? Should I take lots of classes that do conflict with lots of hours? I don't know what to do. So part A of the question is, try this greedy algorithm and notice that it does not work. Prove to me that it does not work. And all you have to do is to show me a set of classes where the greedy algorithm gives you something and some other algorithm gives you something better. And part B is solve the problem for real. And I will reveal the solution technique that you're supposed to use, which is, you thought of a greedy algorithm, didn't you? That means you should use dynamic programming. There is one question on the homework where you really need a greedy algorithm and need to drive through the proof, just because I think it's useful to go through the exercise. But almost every other time that a greedy algorithm pops into your head, it's the wrong answer. And you should use dynamic programming. And only after you have a dynamic programming algorithm written down should you think, well, let's see if we can prove that the greedy thing works. And you might get lucky, but you probably won't. Okay? All right. So I'm going to give one more illustration, but because of time, there is absolutely no way that I can get through the proofs. But because this is such a beautiful application of greedy algorithms, I feel obliged to show it to you. Also because information theory people over in half of your department will probably have shown you this again already anyway. Okay, so what I have here in the middle of the screen is a sentence which reads, truthfully, this sentence contains 3 A's, 3 C's, 2 D's, 26 E's, 5 F's, 3 G's, 8 H's, etc., and only 1 Z. Okay, so this is a sentence that I want to encode somehow. I want to come up with a way of encoding the letters in this sentence with bits to make the length of the encoded sentence as short as possible. Now, this idea of encoding symbols with sequences of bits dates back to the late 1700s when I believe, Gauss was in the 1800s. It was a couple of physicists in Heidelberg who wanted to be able to communicate experimental results to each other across campus. So they built an electrical device where they could throw switches, and they had a 5-bit code which corresponded to letters of the alphabet. This is not actually how Morse code or ASCII or Unicode evolved. But this idea dates back very, very long time. ASCII is an example of a binary code where each of 98 symbols, I believe it is, gets a 7-bit code. There are 32 non-printing things like carriage return and tab and vertical tab and beep that also get codes. But most of the printing characters, 7 bits. This is the character set that C is written in. Unicode is a variable length code, at least with the UTF-8 encoding, where you have a certain number of bits in the beginning of the first byte that tells you how many bytes you need to read. Morse code is also a binary code, but it has a property that makes it bad for this purpose, which it is not prefix free. So the Morse code for E is dit. The 2 bits are pronounced dit and da, dot and dash. The Morse code for E is dit. The Morse code for S is dit-it-it. There is no way, given the sequence of bits, to know whether 3 zeros in a row means S or E-E-E. It is not possible, because the code for E is a prefix of the code for S. All right, so what I want is a prefix-free binary code. So I'm just going to send you a sequence of bits, and by scanning through the bits, when you get to the end of a code, you actually know it's the end of the code because there are no longer codes that include that as a prefix, like ASCII, like Unicode. But I get to decide what the code is. And intuitively, more frequent letters should get shorter code words. This is the reason why E is dit and S is dit-it-it, because there are a lot more E's than S's in English. Okay? So the way that a prefix-free code actually is encoded is by a binary tree, where the symbols are the leaves, and to figure out what the code is, you emit a 0 whenever you go to the left and a 1 whenever you go to the right. So if I want to know what the code is for the letter R, I follow a trail down, 1, 0, 1, 1, 1. Okay? And so what I want to find when I'm looking for this encoding is to find a binary tree that minimizes a certain cost function. It's like the cost function for tape sorting. I want the sum over all characters of the frequency of that character times the length of that character's code. In other words, the sum over all the leaves in this tree of the depth of that leaf times the frequency that that leaf appears. Right? So Huffman, who was the first to solve this problem, I believe as an undergraduate, but at least certainly he was a student, he discovered the following greedy algorithm for this. He said, find the two characters that have the smallest probability, in this case D and Z, and merge them together into a common character, which for purposes of illustration I will pronounce D. Okay? And this is a new symbol that I don't want to distinguish between D and Z anymore, but this is a new symbol that now occurs 3 times. Okay? Now recurs. And when you glue the two symbols together, what you're doing is you're creating this little 3-node binary tree, and now you're treating the root of that 3-node binary tree as a new leaf with its own frequency count. Okay, now the two cheapest ones are L and U with 2 each, and then next is A and C, and then G and Z, and then X and Ru, and then F and V, and then it goes on up. Right? And eventually you build this tree, which gives you an encoding that looks like that. Okay? And the claim is that this is the optimal choice of binary prefix-free code. And the way that Huffman proved this is by saying, I claim that the choice of taking the 2 least frequent letters and merging them is consistent with an optimal code. And moreover, that in the optimal code, the 2 least frequent things are siblings as deep as possible. And then you do an exchange argument by saying, well, if the least frequent thing isn't down here at the deepest possible level of the tree, but it's somewhere else, then I can do an exchange and then argue that that made the encoded length of the message longer. Okay. We are out of time, but the details of the proof are in the notes, as is code to actually build and encode and decode using Huffman codes. All right. Thanks, and I'll see you on Thursday.